This one is January 2021, Unit 4. Which of the following is not a vector quantity? Electric field strength, yes, it is a vector quantity. Impulse is a vector quantity. Magnetic flux is a vector, but work done is a scalar quantity because it does not depend on the direction. A particle of a mass has a m has a momentum of p and kinetic energy ek. A second particle of a mass m/2, so relation p square ek, the kinetic energy is equals to p square over 2m. That's a relation between. So according to this formula, the kinetic energy is inversely proportional to mass. So the mass is half. If the mass is divided by 2, what happened to kinetic energy? It will be multiplied because inverse relation. And kinetic energy is directly proportional to momentum square. So if the momentum is double, what will happen? Kinetic energy increase by 4. So due to change in the mass, it increases by 2, and change in momentum, it increases by 4. So kinetic energy will increase by 8. Is it clear, this one? So when mass and momentum are related by kinetic energy, you always use this equation. Ek, the kinetic energy, is momentum square over 2p. In 2016, an element again was added to a periodic table. One isotope is shown with a symbol. Which row in the table? Number of the protons, so 118 will be the number, and number of neutron, you just take a difference between them. So it will be 176 and 181. 118 and 176, so A will be the right answer. A particle of a mass 3.17, which of the following is mass in giga electron volt per c square? Look, energy in giga electron volt is same as the mass in giga electron volt per c square. So what we simply do, we'll work out the energy in giga electron volt. How to work out energy in giga electron volt? E is equals to mc square. So by using a formula E is equals to mc square, we'll find the energy in giga electron volt. Like we'll convert this mass into joule, and then from joule to giga electron volt, and that will be our answer in giga electron volt per c square. So the mass is there in kg. So this is 3.17 into 10 power minus 27 multiplied by 3 into 10 power 8. When we saw multiply 3 into 10 power 8 square, when we multiply them, what we'll get? We'll get answer in joules. Joules we have to convert into electron volt. 1 joule, 1 electron volt is equivalent to 1.6 exponent minus 19 joules. So to convert joules into electron volt, we'll divide. So this will be divided 3.17 into 10 power minus 27 into 3 into 10 power 8 square and divided by 1.6 into 10 power minus 19. This means your answer is in joules, electron volt. Electron volt to giga electron volt, this gives us energy. But they are, yes, that's I'm saying. Actually, students get confused that they ask, but what we know that if we know the energy in giga electron volt, it is same as the mass in giga electron volt per c square. So actually, giga electron volt per c square is a unit of the mass, but it is convenient to use energy. Why it is convenient? Because we will know how much energy this mass will release. Like if I know the mass of this object is 9 giga electron volt per c square, I will know that it will give, when it will convert into energy, it will give 9 giga electron volt. So actually in indirect, they're asking us how much energy is released in giga electron volt. Because energy released in giga electron volt is same as the mass in giga electron volt per c square. Because as I mentioned, that energy in giga electron volt, if I want to convert a giga electron volt per c square, the mass into energy, then I will do this. But look, the simple concept is that E is equals to mc square. So what we'll do, we'll find this product, we'll get the answer in joules. This answer in joules will convert into electron volt, and the electron volt will convert into giga electron volt. So joules to electron volt will be divided by 1.6 into 10 to the power minus 19. Electron volt into giga electron volt we divided by 1 like billion 10 power 9. That will convert into giga electron volt. And we'll get our final answer in giga electron volt. The final answer in a giga electron volt, they are asking the mass, but what we are doing, we are finding the energy. And because we know that the energy in a giga electron volt is equivalent to the mass in a giga electron volt per c square. So actually from this mass, we are finding energy in giga electron volt, and that is always same as the giga electron volt per c square. If they said convert the giga electron volt per c square, then I will do division by 3 exponent h square. So here the mass is given. So 3.17 into 10 to the power minus 27 multiplied by 3 into 10 to the power 8 square. This will give us energy in joules. Then I divide it. So this will become 3.17 into 10 to the power minus 27 times 3 into 10 to the power 8 square divided by 1.6 exponent minus 19. This will give an electron volt. Then electron volt to giga electron volt, this whole I will divide by 10 power 9. That's why it matches with option D. And this value is actually giga electron volt, but it is also equivalent to giga electron volt per c square. Like let's say this is 20. So it will be 20 giga electron volt per c square. And if they ask, like if they give us a mass in giga electron volt per c square, first what I will do, I will consider, like let's say they said 20 giga electron volt per c square is a mass. Find the energy, convert the mass into kilogram. So first what we will do, we'll say that this 20 mega electron volt per c square will be 20 giga electron volt it will be. And this 20 giga electron volt will convert into electron volt by multiplying by 10 power 9. Electron volt to joules will multiply by 1.6 exponent minus 19. So we get energy in joule. And then we'll use a formula E is equals to mc square. So energy divided by speed of a light. In that case, I'll get the mass in kg. So that's how it is done. So if they ask in a mass in giga electron volt, it's actually you are finding energy. And when they're asking the energy, like the mass in kilogram, actually you are finding energy and then converting that energy into mass. Is it clear? Then a capacitor is there, which one shows a variation of a potential. An uncharged capacitor and a resistor switch. Which of the following shows the charge stored in the capacitor and the potential across the resistor vary? Look, first initially, if this is a 10 volt supply, all the voltage will be here and the capacitor will have 0 volt. But when the capacitor gets charged, the voltage across the capacitor will increase and the voltage across the resistor will decrease because the total voltage is 10 and the eventually like the resistor will be like potential will be there across the, so charge stored on the capacitor or the voltage of the capacitor should increase. So if we sketch a graph for a charge in time, and a potential difference in the time. So potential difference across the capacitor, across a resistor, what will happen to that? The potential difference across the resistor will decrease. Why? Because initially capacitor is uncharged, so less voltage, resistor have more voltage. But voltage across capacitor decrease, voltage across capacitor start to increase as it get charged. So the total voltage is 10. So if this is 1 volt, this will be 9. If this is 2 volt, this will be 8. If this is 3 volt, this will be 7. So the voltage across the resistor will decrease. So C will be the right answer. Positron and muon travel at the same speed through a magnetic field. Positron is a positive particle and a magnetic field is into. My index finger should point into. My second finger represent the direction of a positron because, and I will use a left hand rule. So where my thumb is pointing, so thumb is pointing left. So means the positron should move toward the left hand side. So a movement of positron toward the left hand side. Then when you compare, because they're moving at the same speed, but the deflection depends on the momentum. The one which is having a high momentum will have less deflection, less momentum, more deflection. So when positron is a like a anti-electron, so which is lighter than a muon, because we when we come remember recall the table, you will find. So first thing, positron should move left and it should deflect more because it has a smaller mass or a smaller momentum. Velocity is same, but muon is having a greater mass, so it will have, and it is an opposite particle, negative particle is there, so it will deflect in opposite direction and it will have a smaller deflection because it is having a greater momentum. Is it clear? Question 6. Then the point charges of a 2 microcoulomb and a 3 microcoulomb are placed at 1.2 meter apart as shown. What is the electric field strength at a point labeled X? Look, these are the two charges. Electric field strength we need. Now, what is the direction of electric field? Because it's a positive, so it will be outward. And what is the direction of electric field? It's a positive, so it will be outward. Because like electric field direction for, let's say, 2 microcoulomb is towards right and 3 microcoulomb is toward the left. So they are in opposite direction. So if the two electric fields are in opposite direction, so how to get the result? How we should get the result? We should subtract. If we need the resultant, so we should subtract to get the resultant of the two. Then what is the strength of electric field? Because of 2 microcoulomb, the formula is equals to kq over r square. So if I'm talking about 2 microcoulomb, this will be 9 exponent 9 or 1 upon 4 pi epsilon, because all the value of a k is 1 upon 4 pi epsilon. Q is the charge, so it will be 2 microcoulomb divided by r square. The distance is 0.4, so it's square. This will give the strength of electric field, this value. And the strength of electric field because of a 3 microcoulomb, it will be kq over r square. K is 1 upon 4 pi epsilon. Q is the charge, which is 3 micro, 10 power minus 6, and r is a distance at this point, so which is 0.8 square. Then the one which is a higher value, I'll subtract. It's obvious this will be a, because this is 0, the distance is increased, so definitely the value will be decreased. So B will be the right answer. Like this will be a large value and this is smaller. So as a result, there will be a resultant electric field on point X, which is pointing towards the right hand side. Is it clear? Question 7. Next is a magnetic flux is there, a current. Which of the following is give the current in a wire and its direction? So in the question, the wire is held firmly in place between the two magnets mounted on the top of electric balance. And the reading on the balance is 1.5. When we pass the current, the reading increases. So means the direction, look, if we have a wire, okay, and we have a magnet, magnets are there. Because according to Newton's third law, if the reading has increased, so means the downward force is there. So means there's a downward force on the magnet by the wire and there's an upward force on the wire by the magnet. Because according to Newton, third law, forces always act in pair. If the magnet apply an upward force, the wire will apply a downward force equal opposite downward force. That's why the force has increased. So it means the direction of the force is upward for the wire. Okay. And if we know the direction of the force, which of the four, and we need the current here. We have the poles, like this is a north pole, this is a south pole. So your index finger, left hand rule, your index finger point towards the direction of the magnetic field. Your second finger represent the direction of the current. So if the current is from X to Y, if I take from X to Y, where your thumb is pointing, your thumb is pointing upward. So means in that case, I'll get a force upward. So the direction of the current, what should be the direction of the current? The direction of the current should be from X to Y. Then which of the following, if we need the current, so we have the formula F is equals to BIL. If I need current, so it will be F divided by BL is equals to current. Where this F, don't we need? No, we don't need downward force. What we need, look, we have a magnet, okay? This is a magnet which is carrying a current, which is carrying a current. The magnet, the wire is carrying a current, I mean. Okay. So when the current is passing through a wire, this is X and this one is Y. So when a current passes through a wire, there's a downward force on the magnet. So if there's a downward force on the magnet, there should be equal opposite force on the wire upward. So force on the magnet is downward. That's why the reading on the balance increases. And how much reading of the balance increases? It increases by 0.003. So additional force is 0.003 Newton. So this force will also be 0.003 Newton. So that's why we put here. We'll put like 0.003. B is the strength of a magnetic field, which is 0.07. And L is the length of a wire, which is placed 5 centimeters, 0.05 meter. So we'll get the value for I. Is it clear, this one? So the force on the magnet is downward and the force on the wire is upward. Forces always act in pair. So if a magnet is pushed downward by the wire will push the magnet upward. They both apply equal and opposite forces on each other. Is it clear? Question 9, a 6-volt battery is there. We have a battery connected to two parallel plates. Which of the following shows the electric field lines in the region? As I mentioned, the higher one is always a positive one. So this is 4.5 and this 4.5. So this is correct. Like, then the direction of the electric field is from positive to negative. But here it is given in opposite one. If it's given in B, it is given negative to positive. That's why. So we just work out the higher potential to be positive and its direction is from positive to negative. So D will be the right answer. Here the problem in this one is the direction is not given correctly. A charge capacitor is connected across the resistor and a graph for ln for current against the time is plotted. The gradient of a graph is which of the following gives the capacitance? So you have the formula I is equals to I naught e raised to the power minus T over RC. Okay. If you take the graph is plotted between L and I. So if I take ln both sides, this will be ln I is equals to ln I naught e raised to the power minus T over RC. When in log the two quantities are multiplied, we write them as addition. So ln I naught plus ln e raised to the power minus t over RC. When we further simplify, ln I is equals to ln I naught minus t over RC. Okay. If I rearrange the equation, because the graph is plotted between ln I and t, so this will be ln I is equals to minus t over RC plus ln I naught. Then I compare with the equation of straight line. Y is equals to mx plus c. On y-axis, if I have ln I, on x-axis, if I have t, what will be my gradient? My gradient will be 1 over RC, minus 1 over RC. And if I need capacitance, the capacitance will be minus 1 over um, the gradient times the R, because m is a gradient. So minus 1 over gradient times the R, so it matches with option B. Is it clear, this one? So these are some questions related to Unit 4.